Hello YouTube, this is a talk that I used to do for year 10 and 11 school groups when they visited the University of Cambridge. I've stopped doing it because I've written some new talks, so I'm putting all my slides and pictures and everything like that on the web. This is a talk through of what I used to talk about when I did the talk. Let's get going. So the talk's called Shapes. It's some of my favourite visual proofs of things across geometry. I think that's all I want to say at the start. So here's the first picture I put up. I put this one up, and normally people in the audience have seen this before when I explain this to be Pythagoras Theorem, and I'm going to show them why Pythagoras Theorem is true. I had this kind of impression that everyone would have seen Pythagoras Theorem, but there's this really nice proof that I wanted to show them. So straight away, I've got this slide with some colours on, a kind of colour statement at the bottom there of Pythagoras' theorem that the red area plus the yellow area equals the blue area. And I'm going to try and prove that just using pictures. And I normally say something like, maths is about proving things, it's about working out why things are true, so you should always ask questions when you learn stuff at GCSE or later on in life. Here's the proof that I've seen in some places before. I have no idea who did this first, but I've put it together into these slides. It's something that I think I'd like everyone to see, really, when they learn about Pythagoras' theorem. Here's how it works. You take this shape, which is made up of 4 copies of your right-angled triangle, and there's this blue area in the middle. So we've got one big square on the outside, we've got a blue square on the inside, and 4 of these white triangles around the outside. Okay, so we're going to imagine that these pieces are kind of wooden sliding tiles, like those puzzles you can get where you move the bits around. And we're going to slide those tiles around. I'm going to slide some of these triangles around. Here's how it's going to go. I'm going to slide this bottom triangle up to the top. And if I slide that triangle up, then it goes over here. And I'm going to take the other 2 triangles and I'm going to slide them over there. So this blue hexagon, which has the same area as the blue square originally, leaves me with some more blue area now that's been split up into 2 shapes, and those are both squares. Now the blue area is the same in each of these, so we've got some blue area left over, but it's also clearly made of 2 squares, the squares of the other 2 sides. We could recolour this red and yellow, and because that area, the leftover bit that isn't white triangles inside this sliding puzzle, is the same as I slide the triangles around, it must be true that the blue area is the same as the red area plus the yellow area. And this is pretty much unlike a lot of other proofs I've seen, especially other proofs of Pythagoras' theorem, because most proofs I've seen of Pythagoras' theorem involve writing things down. I've even seen a version quite a lot like this argument, but with some algebra at kind of the last step to chord sides A and B and add things together and square them, write down the areas of the triangles and things like that. Nothing wrong with that proof. I just like this one because it's got pictures all the way through. Okay, so this is Pythagoras' theorem. Red area plus yellow area equals blue area. And I've got a couple more things that I like to show you that have proofs that are just pictures. Okay, here's the next one. Here's a circle, and I've put up this fact that the circumference of a circle is 2 times pi times the radius. And normally at this point, I ask people if they know any other facts about circles. Usually someone in the room will have seen that the area of a triangle is pi r squared. And that's something that you just get taught at some point in school. You just get told that the circumference is 2 pi r and the area is pi r squared. And I try and convince the audience at this point that there's a coincidence there, that both of those formulas involve the number pi. And it feels like maybe in a parallel world they could have different numbers in, that one could involve pi and one could involve some other number. But here they both involve pi, or pi and 2 times pi. I guess those are different numbers but related. So this sort of looks like a coincidence, right? That the distance around the outside of the circle involves this same really complicated number pi as the area of the circle. And when you learn those 2 facts, nobody tells you why those things have the same number pi in them. And there's a nice argument that, again, I can't remember where I first saw this, but it works like this to try and explain why both of those things have a pi in. It works like this. So take your circle and imagine that it's a pizza. Cut it up into lots and lots of slices. If you cut it into really thin slices, like this, then we can take those slices of pizza and we can rearrange them to look something like this. So here I've taken all of my slices of pizza and I've rearranged them into one long line, alternating up and down pointing. At this point I ask the audience, what shape is this? And there's usually someone who's willing to say that that's a rectangle. I mean, it's not quite a rectangle, but it is pretty close to a rectangle. And then I ask, how big is this rectangle? And okay, on one side that's the radius of the circle along there, and along the top, I guess that's half the circumference. Okay, so let's put those on. R and pi times r for the width of this rectangle. So that's what, taking the number pi from the circumference of the circle and using it to label the sides of this rectangle. Okay, but we know how big rectangles are. To find the area of a rectangle, you multiply the sides together. That means we take pi r times r, and the area's got a pi in it, pi r squared. There's a link there between the distance around the outside of the circle and the area of the circle, if you rebuild your circle into this rectangle. At this point I normally do a sort of throwaway comment before I move on to the next one, to say something like, of course if you made the wedges smaller or you used more slices, this would be more and more convincing because it would look more and more like a rectangle. I quite like to put a little bit in that sounds a bit like calculus. Now I'm not quite sure that's a real calculus fact, that if you use smaller and smaller triangles then in some sense this converges to a true argument. What does that even mean? But it's that flavour of having something that tends towards something else, or approximations through this area is made up of these shapes, getting closer and closer the more shapes you use. I like having that kind of flavour involved here, just a little bit, to mention something like calculus. Okay, so that's my second one. Third one, I want to talk about numbers instead. I want to talk about this sum. So from this slide, it's, I guess, pretty obvious when I made this presentation, 5 years ago now, I suppose. So if I want to add up all of the odd numbers between 1 and 2015, I need to do 1 plus 3 plus 5 plus 7 plus, and so on and so on and so on, plus 2013 plus 2015. How big is that? And that's a lot of adding to do. That's a lot of work to do. The pattern so far has been to find a picture that looks a bit like what we're trying to do and use the picture to solve the problem. So I normally let people talk to each other a little bit at this point to find out what they think this sum might be. If there's a quick way to do this sum, I encourage them to investigate it a little bit, I suppose. There's a thing that I normally point people towards. This is a really big problem, this is really tricky, and something that we sometimes do when we're faced with a really big, tricky problem is to look at smaller problems, like it's the year 2015 when I'm doing the talk. That makes the question really hard. If it was the year 5 years after the year 0, when I did this talk, then the question would be really easy, because the question on the board would just be 1 plus 3 plus 5. So just imagine going back in time to the question 1 plus 3 plus 5. If you put that together, that makes 9. We could try 1 plus 3 plus 5 plus 7. That's 16. And hang on, those are both square numbers. And actually, 1 plus 3 is 4. That's a square number. And 1's a square number. So it starts to feel like square numbers might be involved. Or it might just be the square of the number of terms in this sum. And I've got a picture to try and prove why it's a square, to show what the relationship between this sum and squares is. Here's what my picture looks like. So here I'm showing you the sum 1 plus 3 plus 5 plus 7. I've got 1 red square, I've got 3 little yellow squares, 5 green squares and 7 blue squares, and I can stack them together like this. And on the one hand, the total number of squares is obviously 1 plus 3 plus 5 plus 7, but on the other hand, it's really obviously 4 squared. It's 4 along, that's 4 wide, there's a big square, 16. Once you've seen that, I guess it's kind of a proof that we could stack this up with more and more odd numbers on there until we get to the sum that we want to do, which is going to be something like 1 plus 3 plus 5 plus 7 all the way up to 2015. You've got to think a little bit about what the side length of that square is. It's 1008. And then I suppose we've got to go and work out 1008. And 1008 squared, we could do the multiplication for that. Or we could do some sort of binomial expansion, and nobody in year 10 or 11 audiences has heard of binomial expansions usually, but that's some foreshadowing for A-level, I suppose. Cool, I guess it's 1,016,064 or something. Okay, square powers. Right, okay, that's all of the maths that I want to show you. I've got these 3 examples of things where you use pictures to prove things. We saw Pythagoras, where we just got to move some shapes around to see why Pythagoras' theorem is true. In the middle, we had some sort of mysterious link between things like the area of a circle and the circumference of a circle, and now we've got the sum of the odd numbers is the square of the number of terms in the sequence. I really like all of these things. I've stopped doing this talk recently because I think all of these things exist in other people's talks and on the web. I've seen all of these things on brilliant.org. I've seen all of them on Mathagon. And I've got other stuff I want to talk about. And maybe I'll film that one day too. Thanks, YouTube. Bye.